Good evening, student. Today I will discuss about temperature coefficient of resistance. It is denoted by alpha. Already I have discussed about effect of temperature on resistance or resistivity. In case of conductor, if you increase the temperature, then resistance as well as resistivity becomes increases. Already I have discussed this one. In case of semiconductor, if you increase the temperature, resistance as well as resistivity becomes decreases. In case of alloys, resistance as well as resistivity, they are not affected, that is nearly not affected while increasing temperatures. Now I will discuss about temperature coefficient of resistance. Clear? Now, if we assume a given material, that given material which is placed at a particular given temperature, please note it. If you assume a given material, now it placed at a particular given temperature T, while increase the temperature from T to T plus dt, T to T plus dt. Here, at a particular given temperature, a material is placed. While increase in temperature, that becomes T to T plus dt. At a particular given temperature, the material has some resistance that can be represented as initial resistance. It is denoted by R naught. Here, while we increase the temperature, that means T to T plus dt, then resistance also increases. That means R naught to initial R0 to R0 plus del R. Sorry, R0 plus del R. Initially, at a particular given temperature, resistance is initial resistance R naught. After increase the temperature, that is T to T plus del dt, then resistance becomes increases. That means R naught to R naught plus del R, dr or del R. Clear? After observing some observation like as experiment, clear, that dr directly proportional to change in temperature. That means change in resistance which is directly proportional to change in temperature. Also, in practically, we know that dr also depends upon initial resistance. Again I will repeat. In practical view, we know that the change in resistance depends upon change in temperature as well as initial resistance, that is R naught. That means dr, which is equal to some constant quantity. If you remove the proportionality, that can be represented as alpha. That is the proportionality, but this one is the alpha, and it can be represented as R naught and dt. So alpha, which can be represented as temperature coefficient of resistance, temperature coefficient of resistance. Here, it is the main formula of change in resistance, which is equal to temperature coefficient into initial resistance into change in temperature. Clear? From above formula, we have calculated the temperature coefficient for conductor, for semiconductor, and also alloys. What is the value of alpha in semiconductor, in conductor, or as well as alloys? Clear? Now, initially that conductor, initially that material has some resistance R naught at a given temperature. After increase in temperature, that means at a final temperature, the resistance increases from R naught to what? R naught plus dr. That's why change in resistance depends upon change in temperature as well as initial resistance. If you remove the proportionality, then we use a constant quantity that can be represented as a temperature coefficient alpha. Clear? So the total amount of resistance becomes generated due to change in temperature that can be calculated. So in that equation, dr, which is equal to alpha r0 del t or dt is here. Now we integrate on both sides with proper limits, because we have to calculate how much amount of resistance increases while increase in temperature. Okay? After that we have to calculate temperature coefficient of resistance that can be represented as alpha. So here initially resistance is R0, final resistance is Rf, integration of dr, which is equal to integration of initially temperature is Ti, final temperature is Tf. Suppose that can be R0 can be represented as Ri. Clear? Here alpha R0 dt is here. That implies integration of dr can be represented as R, whose integration of dr is represented as R. Initial resistance is Ri, that is the lower limit, and this is upper limit, that is R, which is equal to, here in that case initial resistance remains constant, so taken in all sides. In our book, alpha becomes as a constant quantity because we proved that one. That's why alpha is a constant quantity, but it never as a constant quantity. We assume in our book, due to in book alpha is a constant quantity, we represent in that equation alpha is a constant quantity taken in outside. So Ti to Tf dt is here. So here upper limit minus lower limit, which is equal to, or that Ri can be represented as Ro. Here initial resistance, we already assumed that one, Ro, so that is Ro is here. Clear? So in that case R0 is here, alpha is here. Integration of dt means T from upper limit Ti to Tf. So that means Rf minus R0, which is equal to R0 alpha into Tf minus Tf. So it can also be represented as Rf, which is equal to R0 plus R0 alpha Tf minus Ti, that is the change, final temperature minus initial temperature represented as a change in temperature, that is del T. Clear? That implies Rf, which is equal to R0 taken in outside 1 plus alpha del T. So this is the required expression of resistance while we increase the temperature, that is final temperature. The resistance is Rf equal to initial resistance into 1 plus alpha del T. Okay. Now please note it very quickly. I will erase that one. So in that case Rf, which is equal to R0 into 1 plus alpha delta is 0. Now I will find out the value of alpha. That means RF minus R0, sorry, RF divided by R0 minus 1, which is equal to alpha delta. Because RF by R0, that means plus 1 is here, in the left side that is minus 1 is here, that implies alpha which is equal to RF minus R0 divided by what? That means R0 delta. So this is the final formula of temperature coefficient alpha. From above formula, we have to calculate the value of alpha in conductor as well as in semiconductor and also in alloy. Okay, please note it. Now in conductor, alpha equal to, in semiconductor, alpha which is equal to, in alloy, alpha which is equal to. Now in conductor RF, we know in conductor resistance becomes increases, resistivity becomes increases, because increase of temperature. Increase of temperature, resistance becomes increases, resistivity becomes increases. So that means if you increase the temperature, that is the at final temperature, the resistivity or resistance becomes increases. That becomes increases, that becomes decreases. If you level that one, if you increase the resistance, okay? So that's why alpha becomes increases here in that case. So alpha is positive in nature. So in conductor alpha, that means temperature coefficient is positive because resistance becomes increases as well as resistivity becomes increases. Now in semiconductor temperature becomes increases, resistance becomes decreases, resistivity is also decreases. Now in that case, if you increase the temperature, the resistivity or resistance becomes decreases. So that final resistance becomes decreases as compared to initial resistance. That means alpha becomes negative. So in case of pure semiconductor, the temperature coefficient of resistance becomes decreases. That can be represented as a negative. But in case of conductor, it can be represented as a positive. That is, temperature coefficient alpha always positive in conductor. In semiconductor, alpha becomes negative. That is the very important topic for your exam point of view, and that is the important bit question for you. Okay. In case of alloy, if you increase the temperature, resistance or resistivity both are nearly unaffected. That's why if you while increase the temperature, the resistance becomes not vary, or the resistance as well as resistivity does not vary or does not depends upon the temperature. That means RF minus R0 both are equal quantity. That means whole term becomes 0. So alpha which is nearly equal to 0, because it is nearly unaffected. That means alpha becomes nearly 0 in alloy. In semiconductor, alpha becomes negative. In conductor, alpha becomes positive. Again, I repeat, if you increase the temperature in conductor, then resistance as well as resistivity becomes increases, so that the temperature coefficient alpha is always positive in nature. In case of semiconductor, temperature becomes increases, then resistance as well as resistivity become decreases. That's why the temperature coefficient alpha becomes negative in nature. In case of alloy, if you increase the temperature, then resistance or resistivity both are nearly unaffected. That means alpha, which is nearly equal to 0. Now, so this is the formula of resistance. In case of resistivity, the formula is same. How? That means R can be represented as a rho L by A. That means RF final, which is equal to R0 means rho 0 L by A into 1 plus alpha del T. So L by A cancel out. So rho F, which is equal to rho 0 into 1 plus alpha del T. So in both of the cases, resistance as well as resistivity, whose formula remains same. Okay, that means Rf equal to R0 into 1 plus alpha dt. In case of resistivity of the material, it can be represented as a Rf, rho F equal to rho 0 into 1 plus alpha del T. Okay, so where resistivity can be represented as a specific resistance or resistivity of that material. Okay, so in that case, so and here unit of alpha, that is temperature coefficient, it can be represented as degree centigrade power -1 or Kelvin power -1. Okay, so alpha, whose unit is degree centigrade, whose power is -1 or Kelvin power -1. This is the unit of what? Temperature coefficient alpha. Please student, if any doubt, then ask me, then I will solve that one very freely. Okay? Please subscribe, like and share my video to all. Thank you.